So this set of notes is going to be a sort of a step back and building out some different kinds of data paths than we've seen in other videos, and specifically with the intention of exploring the idea of microcode. This is an idea that students sometimes have trouble with, and so I want to build this out separately, mostly because the machines that we built out for ARM and for MIPS and for LC3, well, LC3 does have microcode in the machine that we built, but for RISC-V as well, these machines are very, very simple and straightforward to build because they're a single cycle, right? Everything happens at once. But in reality, we have machines that take a few cycles to accomplish an instruction, and so this set of notes is about how that works. We're going to first talk about the difference between Harvard and von Neumann architectures, which you've probably seen before. Introduce a very simplified instruction set architecture, talk about how memory might be accessed and isolated, and then build a few different variants of machines that can accomplish regular instructions using a sequence of micro instructions. There's going to be a basic fully connected machine, and then there's going to be machines that have bus architectures, single bus and multibus, and then we can see the differences in the way those things work and the differences in the way that the microcode is implemented. So let's talk about all those ideas. First of all, the idea of the difference between Harvard and von Neumann architectures. There's a lot of little fiddly bits that are different between these two approaches to building a data path, but fundamentally, it's about where information is stored. And in the Harvard architecture, instructions are considered separate from data. They're very different things, and they're stored in different places, and they're accessed in different ways. Whereas in a von Neumann architecture, all data is the same. Instructions are data just like data is data. And so you put it all in one big place, and that has some advantages and disadvantages, right? You can manipulate instructions as if they were data, which leads to like dynamical programming and a lot of other really cool stuff you can do. But you can get into real trouble because if you put something that is supposed to look like an instruction but doesn't, and then you try to read that as if it were an instruction, it doesn't work, then you have to figure out how to handle that exceptional case. And we'll have ideas about exceptions and interrupts and traps and stuff later on. So the basic Harvard architecture, because it separates everything out, we can actually do everything in a single instruction in a single clock cycle. And this is what we've seen in the RISC-V architecture and other videos and other places, where we have the program counter addresses instruction memory, and then right out of instruction memory comes an instruction, which then directly addresses the register file, and then right out of that comes the data that is presented to the ALU and then directly addresses the data memory, or is written back to the register. All feed forward, one thing after another. Really simple, really straightforward to understand, and super easy to control because there's very few choices to make. Everything just happens, right? The problem is there's no opportunity to reuse any element you might need to reuse. So, for example, in a typical load store instruction, you have 3 different kinds of addition type operations. You have to increment the program counter, and you have to calculate an effective address, and you have to actually do the operation, the add or subtract or whatever. Right? Those are 3 different things that you could use the ALU for, but if you're not careful, you may have to actually implement 3 separate ALUs so that all of those things can happen at the same time. And when we pipeline a machine, of course, that's what we end up having to do anyway. But in the early days of constructing computers, there was, building an ALU is expensive and difficult. Memory is big and complicated and expensive. And so you build one thing and you want to be able to make use of it over and over again in different contexts. So the single ALU might do multiple things in a single instruction. For that to happen, the instruction has to take multiple clock cycles. And this is where we get into the idea of how do you control which bits of the data path do what at what times. And then we introduce the idea of microcode. So a von Neumann machine has everything in one place. There's just a memory, and instructions and data and everything live in that memory. Harvard machine, we separate that out, right? And so when we build these data paths in this section, in this unit, we're going to build a von Neumann machine where everything is stored in one place. And then we're going to compare that to what we built of the Harvard machines, like you can see here, where things are stored in different places and everything does its own job. In reality, in the real world, everything is a combination of both. And this is a theme in computer architecture, is that you take the best ideas from all these different philosophies and you build something that is sort of functional for what you want to do. So in the real world, L1 cache, level 1 cache, is typically separated, just like in the Harvard architecture. But main memory is typically integrated, just like in von Neumann architecture. So it's a bit of both. It's a flavor of both. So we're going to build some von Neumann architectures because that's the easiest way to introduce a machine that we can then explore for microcode. And microcode then, what the heck is microcode? When we build out one of these machines, we have to control each element of the machine to make it do the thing we want to do. The individual control points, which is just a single signal, a wire that says do the thing or don't do the thing, or maybe it's a collection of wires that says to this multiplexer make this choice or make that choice. Each one of these we have to build out and tell it to do the thing. Microcode is a collection of these control points and their values for each clock cycle in the execution of a larger instruction. It'll be easier to understand once we actually build this out and show it to you, but the idea is because we're going to reuse the ALU multiple times, reuse the memory multiple times, it takes multiple clock cycles to do that, and in each clock cycle, we have to specify what each element of the machine is going to do. That's a micro instruction. And then we're going to have a little tiny micro finite state machine that's going to tell us we do this, then we do this, then we do this, and that's our microcode. So that's the whole idea. One of the key features of this is to make memory accessible for whatever we need it for, right? For instructions or data or anything else. And we want the access to be as consistent as possible so that it's as easy as possible to understand, build, and program. To do this, we isolate the memory. So in von Neumann architecture, we typically isolate the memory by producing two registers on either side of the memory. We're going to have a register at the address input so that we can put an address there and to specify whatever we want to look for. And then a register on the other side where we can access data. And that is either giving data to put into the memory or receiving data from the memory. These two registers basically isolate the memory and allow it to operate independently of other units. We typically call these MAR or MAR for memory address register, and MBR or MBR for the memory buffer register. Other architectures sometimes call this the memory data register. So you'll see me using those interchangeably. In the LC3 set of notes, I believe this is the memory data register, but it's the same idea. So we isolate memory access using MAR and MBR. And I just want to introduce this idea first to give you this flavor of each element in the machine is going to be done separately. So we've got the idea of a von Neumann architecture where any element in the machine could be used in multiple different ways for multiple different purposes. And then we've sort of introduced the idea of microcode. I got one more thing in this introductory video, and then in the next video, we'll actually build something out. Is that I don't want to do this for like a big complicated machine language because, you know, every modern machine language is incredibly complicated and has a lot of little bits and fiddly details. And we can build one of these things out for a real language like RISC-V or MIPS or ARM if we want to. But for the purposes of the microcode conversation, it's easier if we condense all the way down to something as simple as possible. And the key features for any assembly language, just like we've seen before, are moving data around, so loads and stores, doing some math, in this case we're going to add and subtract, and then making some choices, branching and branch equal. So we've got a direct branch, an unconditional branch, and a conditional branch. And you'll notice here, we've actually only got two registers. This is going to be a super, super simple assembly language. And it's fully Turing complete. It can do everything. But it is going to take a lot longer to do some things than others, right? Because we've only got two registers, we've got the memory access. And so we're going to have the opportunity to put an address into the memory address register. This is the load instruction. And then look up what's there, and then move that into a register. Alternatively, look up what's there and put something into it, that's the store. And then we have our add, which is to add the two registers and put them into register 1. And the subtract the two registers and put it into 1. And the really nice thing about this assembly language is that it's as fully specified by the opcode. We don't need any operands except the memory address. We'll get to that in a second. We don't need to say what registers we're using because opcode 000 is loaded into R0 and 001 is loaded into R1. So it is a very, very simple assembly language, and that lets us do some really interesting things with the machine. So I'll give you just a snapshot of the machine as we're going to build it out. and then we'll start the next video from there into the next version of the machine. This is what it's going to look like. This is our first pass of the machine. So have a quick glance at this, and we'll start the next video at this point.